No, I told you. She doesn't want to be in my city. Well, what are you doing? Get out of there. You didn't want to be held like that. Stop yelling in the background. Now I have no idea what we're doing. Find the power series. Find the A power series solution for y prime prime 2y prime prime plus xy prime plus y equals 0 about the ordinary point x naught is 0. Is it analytic there even? Yes, analytic. So this guarantees x naught is an ordinary point. So what we're going to be doing, again, I'm not even introducing her. She's being a jerk. She's trying to attack me. That's Willa again. She's trying to screw with the lighting and everything else and ruin everything as we try to make videos. So what we're going to do this time is, this one's going to take quite some time and it's got quite a few moves in it, but we're going to try and find the power series solution to this about the ordinary point, or the Maclaurin series about centered at x naught equals 0. So you do the pre-prep for this. My functions are 2 and x, and so even if I divide by that, I don't have x0 is an ordinary point, is not singular. All the power series are going to be analytic, so there will be a power series solution, and there will be 2 linearly independent solutions, both with power series about x naught equals 0. So there will be 2 Maclaurin series I create from this scenario, from this ODE. So I'll show it once, and then in the map they're now fighting each other. I want to eventually spin cameras to where it's like we've got boxing octagon match of several different cats in several different rounds happening right now in the background. We also do cat fights. Cat fights! I don't think that's a thing. That's probably illegal. Oh, cat fights. So, if you've done this or you're trying to attempt this before, if you've tried this at all before, what we're going to do with that is we guess that our power series y is a power series from n equals 0 to infinity of a n x to the n, x minus 0 to the n. So that's I'm using the Maclaurin series. So we guess our solution is this. Then already, we need a bigger board because I'm going to run out of room already. So put that in the budget or set. I don't know who I delegate that to, but not me. It's going to be me. I'll have to do it. When I take the first derivative, what's going to happen is I bring n down, but now that n is down in the power series, we notice that the first term will be 0, so they re-index. This is the sum from n equals 1 now of a n x to the n minus 1 to infinity. And then when I take the derivative of this, I'm going to get n minus 1 down, n minus 2 by the power rule again. This is term-by-term differentiation in the power series. And once I do that, you can see that y prime prime is going to be equal to sum from n equals 2 to infinity of a n minus 1 x to the n minus 2. Don't worry, I'm going to squeeze that in already, but I see bigger whiteboard necessary. So every time we do this, especially when it's second order, you need to guess that your power series solution looks like this. Then I take the first derivative. It starts at 1. Yes, it changes. Technically, you could make it 0, but then a0 will be a 0 at first. Leave it as the 1. And then we start at 2 for the second degree. Now we're going to put that into here and simplify. So the first stage is make these guesses, have the derivatives. They always look like this every time, unless they change the center. But if they don't do that, now what we're going to do is take these things, put them in there, simplify. That's step 1. Take these, simplify. So now that I have the original ODE and I have in mind what the power series and its first derivative and second derivative look like, I put them in there. That says I will have 2 times the sum from n equals 2 to infinity of a n minus 1 x to the n minus 2 plus x times the sum from n equals 1 to infinity of a n x to the n minus 1 plus the sum from n equals 0 to infinity of a n x to the n equals 0. Just made it. Now, what we're going to do with that is we're going to simplify it. Any powers that I have, what that actually shows you in the dirty trick here is when I have this, if they put an x squared there, well, it wouldn't have been analytic about 0, so we couldn't guarantee 2 linearly independent solutions. So that's usually why they haven't done that at first. But if there was an x squared there, and they say that there is a power series solution, I wouldn't have to simplify or re-index this, because the x squared on the outside and the n minus 2 missing would combine. And so they were nice to you here and put one there. By putting the x there, I can already see that those are going to combine, and I will have x to the n, and we won't have to re-index that one. This x and this negative exponent are going to cancel, and I'll just have x to the n. And this one didn't have anything, so it won't be raised up. So I don't have to index shift this, and I don't have to index shift this. I will have to index shift this one. I'm jumping the gun a little bit. Simplify. This is the sum from n equals 2 to infinity of 2a n minus 1 x to the n minus 2 plus this and this cancel each other. This is x to the negative 1 times x to the 1, which are going to cancel, which gives me the sum from n equals 0 to infinity of a n x to the n, which I won't have to re-index, plus the sum from n equals 0 to infinity of a n x to the n equals 0. Now, that's the first stage. Take your 3 guesses, put it into the ODE, and simplify everything. Now that we've done stage 1, we have are ready for stage 2. Now what I look at is the next stage is re-indexing the powers of x. These all have to be x to the n's, and this one isn't. So that term has to be re-indexed. These ones don't. So how do I re-index? What I do is I call it, it's a dummy variable, so I'm going to call it m. I'm going to re-index so I can shift everything in this power series. And because m was dummy, I'm going to turn it back into n so I can combine everything. That's weird at first, so what I'm doing is I'm going to call it m. How do you do this? He's the bad exponent, and I want it to just be n. So I pick a new variable, m, and I see that's equal to n minus 2, the thing I don't want there. And then when I replace it, it'll be just a m instead of an n minus 2. But now I have to get rid of everything else. I have an n minus 1 and I have an n, and then we started somewhere. So you have to take care of that. From here, that says n is m plus 2. And then if I subtracted 1 from this, n minus 1 would equal m plus 1. And now I can get rid of this and these 2 indices. And the last thing I have to do is, if we started at n equals 2 in this power series, where does m start? M will start at 2 minus 2, which is 0. So now that I have that, I can liquidate n and put all m's in there temporarily, which I'll do over here, and then we'll reshift, and this will be shifted and put back into the exponent n. So I'm cleverly going to turn it all into m's, but then because m is dummy, I'm going to put n back in. So this says the sum from n equals 2 will be m equals 0 of to infinity of 2 times a m plus 2 times m plus 2 times m plus 1 x to the m. And that's what the clever indexing shift did, is now I have a power of a single exponent. I don't have any minuses in there or pluses in my exponent. So what that now did is, what that re-indexing does for me is I can now re-index this and all the exponents are the same now. So that gives me the sum from n equals 0 to infinity of, where'd the 2 go? Nowhere. 2a n plus 2 n plus 2 n plus 1 x to the n using the dummy variable. And I already have to fit these ones in there now. Plus the sum from n equals 1 to infinity of a n x to the n plus the sum from n equals 0 to infinity of a n x to the n equals 0. So now we've re-indexed the terms that we needed. So all of the exponents are now x to the n. That's the end of stage 2. Stage 1 is make your guesses, take the first derivative, take the second derivative, put them into the equation, simplify. Stage 2, re-index. Anybody who needs it, this, you can stop the video or watch it several times to see how the clever indexing shift works, but you have to, that's never going to change. You have to change all the terms so that the indexes now become all x to the n's. Now that I have that, what's the next stage? Everyone forgets this one too. When you do the index shift, rarely are these starting at the same point. And now we're going to have to do that again. And this also really hurts your brain at first because you have to open up these things. This one starts at 0. This one starts at 0. They're sequence values. I don't know what they are, but they're representing they start at 0. But this one starts at 1. He has no 0 term. So if I want to put these all into 1, I can't do that if they start at different indexing, and you're like, well, now what am I going to do? Just, it's the low one you have to focus on. The higher one doesn't need to change because he has this. I can never give him more terms to go backwards. What I can do with this one is take those terms off and make them start at 1. So now this one and this one, I have to take off the 0 term. So because the indices aren't the same, what we're going to do is I have 0 and I have 1. And then I have the other sequence terms, but it doesn't matter. These two start at 0, so they have some value. I don't know what they are. There's 2 of them. But this one only has, this sequence or series only starts at 1. It doesn't have a 0 term. So what I'm going to have to do is take them off. So when n is 0, what I have to ask myself is, what does this term look like and what does this term look like that I steal off of there for this? So when from this term, when n is 0, the 0 term is going to be 2 times a2 times 2 times 1. I just put n equals 0 into there, x to the 0, which gives me 4a2. That's the Hindu 4. They're all Hindu numbers. That's a different story. 4a2. From this one, when n is 0, what do I steal? I'm going to steal just an a0 x to the 0. So that's what I'm going to steal. Why did I get a plus? Because I'm still going to be adding them into the equations. Everything's adding in these series. So long story short, what I'm doing is the index is starting at 0s and at 1s. The higher one I have to leave alone because he doesn't have lower terms. What I do is I steal the 0 term from those 2 guys so that they'll all start at 1. So now what that's going to do, and those were the 2 terms, I cooked them up ahead of time. Don't try to do it in your head. I recalculated what they were first. Now I'm taking them off. So the next stage is, essentially what I'm doing is, stage 3 is just a mini stage, but it's extremely important. Steal off the terms that are below the index where the highest one is. So if you started at 2 or 3, you would have to take all those terms off until you start, so that they all start at 3. Here we have 1, so we steal the 0 terms. What does that give us? That now gives us a0 plus 4a2 plus all of this. But now the key is they all start at 1. The sum from n equals 1 to 2an plus 2 n plus 1 n plus 2 x to the n plus the sum from n equals 1 to infinity of an n x to the n plus the sum from n equals 1 to infinity of an x. Whoa, where are you going? X to the n equals 0. So I've stolen off that mini stage. Stage 3 is steal off the first term so that they all start now at 1. Now what that says is, because they all start at that, I can combine the sum of the sum of the sum is the sum of the sums. There's a bunch of sums in there. We're going to add the sum of these things. So, bear is in the way. So this is a0 plus 4a2 plus the sum from n equals 1 to infinity of, now I can combine all of this, 2 an plus 2 n plus 2 n plus 1 plus, oh I see it, but can you, I have an n and an 1, so I can factor that. That's an n plus an x to the n equals 0. I've combined all the terms, and this one I really want to do quickly because I'm lazy and I'm not writing that out again. There's an an in both terms, factor it out. It's an times n plus 1. now that I've done that, what this says is, the dirty trick here cleverly is, this is the power series 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 forever. Infinity is I'm going to steal a Woody Allen quote now. Infinity is an extremely long time, especially towards the end. Especially towards the end. So, what that says is I have infinitely many zeros on this side and infinitely many terms on this side. What that says is, because this power series equals this power series and this one's 0, all the coefficients of the power series have to be equal, which says all of these terms are 0. And that's where we get our recursion relation from, is from the fact that all of these have to equal 0. So first of all, what does that say? This is also 0. But they're not both 0. All I can tell is that their sum is 0. So be careful. Sometimes if you just get one, you can conclude that he has to be 0, but I have 2 of them. So what does this say now? From this statement, all of these are 0 and this is 0. That's what's 0. So this is 0 and all of those are 0 for every n. Let's write that out. Also, what's really good when I write that out, I'm going to switch from n to a variable k, because something weird is also going to happen now, which really is going to hurt your brain with indices. So I have 4a2 is negative a0, or a2 is negative a0 over 4. And now I'm going to switch to k. So k is going to be, this says 2ak plus 2, k plus 2, k plus 1, plus ak, k plus 1 equals 0 for every k larger than or equal to 1. I switched to k because n is what I want in the power series at the end. I want a sum from n and a sum from n, but n is either going to be 2k even or n is going to be either 2k odd. So I want to look at the k inside the n, because I have to talk about now the index n being even or odd, which means n depends on k, whether he's 2k or 2k plus 1. That makes it worse. They weren't hard enough. There has to be this index shift and then index variables of whether n is even and odd. What I'm going to do with this is, now that I have this, we solve for the largest index in terms of the smaller index, and we get a recursion relation, which was good. From this, immediately, you should factor it out. I shouldn't do the lazy rule while I'm trying to do a tutorial video. K plus 1 is in both terms, so I'm going to factor it out. 2 ak plus 2, k plus 2, ak plus ak equals 0. So I can get rid of that. Don't be lazy unless you see it. That's what I was going to do, but factor it out is the safer move, and then you can't get it wrong. Now, this says that ak plus 2 is equal to negative ak over 2k plus 1. I just solve for ak plus 2. So I bring this one over, it becomes negative, and then I divide by 2, and I divide by k plus. Ooh, that would have hurt in the recursion relation. K plus 2. So, now that we have that, I have a recursion relation for k larger than or equal to 1 for ak plus 2 dependent on ak. And we have a starting point also. Which also becomes weird at first is, what this says is we're going to find a power series for odd ans and even ans, so a2k and ak, but right now the ak's are listed in this recursion relation to find them. So I'm going to ignore the fact that I'm looking for even ones or odd ones at first, and I'm just going to use the k's to find out what those even and odd guys look like. And then once I have a list of a bunch of them, I'm going to try and find the pattern or the recursion relation for the general a2k when you're odd or when you're even, 2k plus 1 or 2k. Then once I have that, they all depend on, the recursion relation ends up having them all depend on the starting point a0 or a1 when you're odd. So what we're immediately going to do is a0 is going to be any real number, and a1 is actually going to be any real number, because we won't be able to tell from this scenario what they actually are. They're free to be anything. And those are actually going to be the two coefficients in front of the two linearly independent terms once we're done. So that's also painful at first for your brain. But we can't narrow down what a0 is. a2 already depends on a0, so a0 will be free, and we can't find out what a1 is, but we can find out what all the odd guys are based on those guys. So now let's do that. I'm going to rewrite magically this recursion relations one more time and compute a whole bunch of values to find a pattern. So now what we're going to do is try and find a pattern. Never combine two negatives to cancel them, because then I can't see they were there anymore. When you get two negatives, that's -1 squared. When you have three negatives, it's -1 cubed. You keep everything. 2 times 2 is not 4. I don't even like that. That I'm already going to suspect is 2 squared somehow, or I don't know, but you want to open everything up. I'm trying to find patterns. If you simplify all the numbers, what they trained you for K to 12, just put everything. No, that's the reverse of what we want now. All that energy to try and simplify and group everything together now finally has to be done in reverse. Never simplify, never group any of those things together. I'm trying to find a pattern in what's happening based on the index. So first of all, I'm going to use a bunch of K's to find out what a bunch of the A values are. So just put a K in there, and this says K I can start running K from 1 or higher, and then we're going to find a bunch of the A values. Then we'll stop and reassess and ignore K. We're going to drop K like it's hot. So when K is 1, I get A3, 1 plus 2. So that gives me A1 plus 2, which is A3. From the recursion relation, A3 is equal to -A1 over 2 times 3. And again, we can't narrow down what A1 is, so he's going to be arbitrary, so we're going to leave it like that at first. When K is 2, this gives me A2 plus 2, which is A4, which is A4 is, from the recursion relation, -A2 over 2 times 4. But A2, I already know what A2 is. A2 is dependent on A0 already. So that says now that this is -1 times 4 times 2 times -A0 over 2 squared. So what is that? I'm going to combine that and clean that up. Remember, never combine those. That's -1 squared A0 over 2 squared. I'm going to leave that. And then what I'm already seeing is, if you can't see it, these are both even. They both have a 2 in them. So that will be 2 squared again times 2 times 1, which seems an awful factorial-ish, but let's compute just to see. When K is 3, I'm going to get A3 plus 2, which is A5, which is, from the recursion relation, -A3 over 2 times 5, which is equal to -1 over 2 times 5 plus, or times, sorry, A3, which is this one, -1 over 3 times 2 times A1. This pattern's a little harder to see. Can you see it? This is now -1 squared, 2 squared over 5 times 3 times 1, A1. I see the pattern. Let's do one more. We'll do K equals 4, and then can you see the pattern in both? And then we'll meditate on this. There's a whole lot going on. This solving nonlinear recursion relations. Engineers could do it. They don't even point out that I could spend about a month in a discrete mathematical class talking about linear recursions and nonlinear recursions and their general solutions. They're just throwing it at you, and this is one of the steps in solving these ODEs. That's what's happening right now. Holy crap. So K equals 4, that gives me 4 plus 2, which is A6, which is, by the recursion relation, which is nonlinear, A4, -A4 over 2 times 6, which is -1 over 2 times 6 times, I already cleverly figured out what A4 was, so that gives me, again, -1 squared over 2 to the 2 times 2 to the 2 times 2 times 1. I've done this before. You can clean that times A0, clean that algebra up again. What did I get? I now have, steal a 2 from the 6. That gives me 2 to the 3 times 2 to the 3 times 3 times 2 times 1. I know I squeezed that in there. I'm going to clean it up again and show us what the general formula is anyway. So what I basically do is I compute enough of these till I think I see a pattern. You have to practice a few of these to start seeing the patterns in these recursion relations. But notice again, what's happening is all the recursion an is eventually, if it's even, it's going to depend on a zeros. And if you're an odd index, you're going to end up depending on a1. And then, because every term in the series is going to depend on a0 or a1, those will be the two linearly independent solutions that we get from those starting points. So I'm going to keep these. Let's get rid of everything else. From those calculations, this said, let me write that down. A5 is equal to negative 1 to the 2 over 2 squared times 5 times 3 times 1, a1, and a6, I said, is equal to negative 1 to the 3 times 2 to the 3 times 2 to the 3 times 3 factorial times a0. And now here's what you have to do one more time to see it. Can you see what's happening here? This will help a lot. A5 is 2 times 2. I want to look at the index and see what happened. 2, 2, 2. Where's the 2? I want to match that. And then there's 3's everywhere. 6 is 2 times 3. So 3k is 3, 3, 3, 3, 3. Oh, I see a pattern. So I'm going to say that, and we would have to actually prove this by mathematical induction, which they don't also. Maybe we can crush that out. We'll do this one in another video. I'll prove that these are actually the formula for every n by induction. What's mathematical induction, you ask? Good question. Next video. So from this, I suspect that a2k plus 1 is going to be equal to what? a2k plus 1 is, when I had a k here, this is the k. So when I had k as 2, I had negative 1 to the 2. So I'm going to get negative 1 to the k times a1. And then I had 2 to the 2, so that should be 2 to the k. And now what's 5? 5 is also 2k plus 1, so this will be 1 times 3 times 5 times dot dot dot. Where do I stop? 2k plus 1. There's now a closed form for that recursion relation. We're going to clean that up even better because we're going to make it into all factorials. Just wait. From this one, a6 is 3, k is 3. This says a2k is going to equal negative 1 to the k over 2 to the k times 2 to the k, or 2 to the 2k, or that's actually 4 to the k, because 2 to the 2 is 2 squared, which is 4. Either way, I'm going to leave it as 2 to the 2k times k factorial times a0. That gives us our coefficients. And now, just as an aside, 1 over 3, 1 times 5 times 2k plus 1. This would be a factorial, but it's only the odd numbers multiplied. It's missing all the even numbers. Well, I'm going to just put them back in then. 2 and 4 and 6 and 2k. Let's go. And you're like, that's crazy. You just... No, it's not, because I'm going to use my favorite dirty trick. I'm going to multiply by 1. Now, this makes me happy already. What do you see? Can you see it? On the bottom, I have the product of every number from 2k plus 1 down to 1. So on the bottom, that's 2k plus 1 factorial. And now here, each of these has a 2 in them, and there's k of them, so I can take a 2 out of each, and that'll give me 2 to the k. And what will be left? 1 times 2 times 3 up to k, which will be k factorial. So that is actually equal to 2 to the k factorial over 2k plus 1 factorial. In the last step, now that we've used the k's and we had to do all that, it's solving the recursion relation. Now that we have everything, we have, for when n was odd, this would be an, when n is odd. No, so now for every index n, for every integer, if it's odd, the coefficients of the power series looks like this, and it depends on a1. If n is even, it'll be 2k, and the coefficients will look like this. So now if you want, what I'm going to do is now I'm going to write the power series general solution of this ODE originally, it should be y1 of x plus y2 of x, which is equal to the sum from n equals 0 to infinity of an when n is odd is going to be, this is the n. So I'm putting n where k is now. This is negative 1 to the n, 2 to the n, n factorial over 2n plus 1 factorial times a1 x to the 2n plus 1 plus the sum from n equals 0 to infinity of negative 1 to the n over 2 to the 2n n factorial over a0 times x to the 2n. These are linearly independent. I can take this out, and this is a constant, so I'm going to rewrite it one more time. The general solution to that original ODE, the original ODE was 2y prime prime plus xy prime plus y equals 0. The general solution to that is y of x equals a1, or let's use a0. a0, the sum, I don't know what that was. The sum from n equals 0 to infinity of 2 to the 2n n factorial, negative 1 to the n x to the 2n plus a1, the sum, no, I wanted that on one line. Now I erased the power series. I have no idea what the power series was anymore. So the solution is y of x equals a0, the sum from n equals 0 to infinity of negative 1 to the n over 2 to the 2n n factorial x to the 2n plus a1, the sum from n equals 0 to infinity of negative 1 to the n 2 to the n n factorial over 2n plus 1 factorial x to the 2n plus 1. We need a bigger board. The general solution, power series solution, centered about the ordinary point x naught equals 0, or the Maclaurin series. Because this is because x naught equals 0 was an ordinary point, this ODE is guaranteed to have two linearly independent solutions in its general solution. Step 1, what we do is, to recap, we guess the power series and then we take the two derivatives. We put it into the ODE. We simplify. Step 2, we re-index any power series that need this so that they all have x to the n's. Once I have that, step 3 is baby, but really important. You need to steal off the first few terms so that they all start at the right sum. In this case, it was n equals 1. Then once I do that, I can set them all equal to 0, get a recursion relation. In that, there's several steps in there. I can probably do some videos just on recursion relations to show you how to just deal with this. We'll do those ones specifically, or we'll just start with those recursion relations. Basically, in that recursion relation scenario, what you want to do is find the first few terms, find the recursion relation, write out a whole bunch of them so you can try and find a pattern. Once you think you have a pattern, you split it into possibly an even case and an odd case, depending on what's happening, and then you find all the coefficients. Technically, you should prove that by induction, but they never do. So then what I do is, because of that, I have two linearly independent solutions based on those recursion relations, based on whether n was odd or when n was even or n was odd. So to recap, the two linearly independent solutions in the general solution to that ODE are 2n plus 1. This power series and this power series, both centered about 0. I never remember doing any of that crap. Do the crap below where you're supposed to subscribe to my channel and like this and hit the bell, or I don't know which one means anything. Subscribe, definitely. See you next time.
Yeah, we're at like 25 minutes almost altogether right now. Maybe 20. There's a lot to edit out.
People will watch these